We all know black holes as terrifying cosmic entities, places where matter gets trapped forever, sucked into an inescapable abyss. It's a compelling image, but it's only half the story. In fact, black holes are also crucial cosmic engines, shaping galaxies, regulating star formation and driving some of the most dramatic phenomena in the universe. Black holes exist throughout the universe, lurking in the hearts of galaxies, speeding through interstellar space, and even haunting the surfaces of neutron stars. To understand them, we need to look at how stars die. Our sun will eventually run out of fuel and collapse in on itself, becoming a white dwarf. If it were bigger, say 10 times the mass of our sun, when it collapsed, it would collapse further, creating a neutron star. Keep increasing the size until you get something around 20 times the mass of the sun when it collapses. Nothing can stop it from collapsing all the way to a black hole. There are two main types of black holes, stellar and supermassive. Stellar black holes are relatively small, ranging from a few to several dozen times the mass of our sun. These are the celestial underdogs. Born from the dramatic deaths of massive stars, when these giants run out of nuclear fuel, their core implodes, collapsing under its own gravity and creating a black hole. Supermassive black holes, on the other hand, are millions or even billions of times heavier than our sun. Their origins are more mysterious, but their influence is undeniable. Most galaxies, including our Milky Way, harbor supermassive black holes at their cores. These giants are not just massive, they are also incredibly dense. A typical supermassive black hole might be 100 billion kilometers in diameter, yet it packs the mass of several hundred billion suns into that space. The result is a gravitational pull so strong that not even light can escape their grasp. Once it crosses a certain point of no return called the event horizon, here that black holes truly earn their fearsome reputation. Anything that ventures too close, be it gas, dust, or even light, gets pulled in and can never escape. Once inside the event horizon, the rules of physics as we know them break down. Time stops, and space becomes infinitely distorted. We can't see inside black holes, so we can't observe what happens after crossing the event horizon. What we can observe is what happens around the black holes. And there we see evidence of extreme heat, powerful jets of particles shooting out of their poles, and vast glowing clouds of hot gas swirling around them. As matter falls into a black hole, it speeds up and heats up dramatically, emitting huge amounts of radiation. This makes black holes true cosmic engines. They drive the dynamics of galaxies by pulling in and flinging out vast amounts of matter. The immense energy released in the process can trigger star formation, regulate star formation, or even destroy entire star systems. Black holes are not just cosmic powerhouses. They are also cosmic laboratories. They allow us to test the limits of physics in extreme environments where gravity is thousands, if not millions, of times stronger than what we experience on Earth. Studying them gives us clues about the fundamental nature of our universe. By observing how light bends around black holes, for instance, we can learn more about the nature of gravity. Our Milky Way galaxy is home to a supermassive black hole at its center. It has a mass of about 4 million suns and is located in the constellation of Sagittarius. While it's not as massive as some of its counterparts, it plays a vital role in the galaxy's structure. Its gravity keeps our solar system and the rest of the galaxy in check. But it's not just a celestial bouncer. It's also a key ingredient in the production of new stars. The black hole at the center of the Milky Way, along with a collection of gas and dust, forms a sort of cosmic nursery. As material swirls around the black hole, it forms a disk. This disk heats up to extreme temperatures, emitting huge amounts of radiation that can trigger the formation of new stars. So while black holes are often portrayed as cosmic vacuum cleaners, they're actually essential for the creation of new life in galaxies. Understanding how black holes form, evolve, and interact with their surroundings is crucial to unraveling the mysteries of our universe. From the smallest stellar black holes to the giant supermassive ones, these enigmatic objects are not just destroyers, but also engines and laboratories. They shape galaxies, regulate star formation, and allow us to test the limits of physics. As we continue to explore the cosmos, one thing is clear: black holes are much more than meets the eye. They are the key to understanding the fundamental structure and evolution of our universe. In the grand theater of the cosmos, there are few scenes as dramatic as the birth of a black hole. It's a moment when the very essence of existence is pushed to its breaking point. And to truly understand black holes, we must first confront this process that gives birth to them. We must unravel the secrets of how matter is transformed into the most extreme and mysterious objects in the universe. At their heart, black holes are the natural consequence of gravity taken to its ultimate extreme. Every star in the universe is engaged in a delicate tug-of-war. On one side is gravity, pulling inward, trying to crush the star into nothing. The other side is radiation pressure, produced by nuclear fusion in the star's core, pushing outward. For most of a star's life, these two forces remain balanced. Gravity pulls in, fusion pushes out, but this balance is temporary. When massive stars, at least 20 times the mass of our Sun, run out of nuclear fuel, fusion comes to an end. With no outward pressure to counteract gravity, the core collapses catastrophically in a fraction of a second. The result is a supernova explosion, one of the most powerful events in the universe. The outer layers of the star are blasted into space, seeding galaxies with heavy elements like iron, gold, and uranium, elements that would one day form planets and life itself. But what remains at the very center is something far stranger. If the collapsing core is small enough, it stabilizes as a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons. But if the collapsing core is too massive, even neutron degeneracy pressure, the last quantum resistance of matter, cannot halt gravity's pull. In this case, collapse continues without limit, and a black hole is born. So how massive does a core have to be to cross this threshold? To answer that question, we turn to the life story of a star. Massive stars burn through their hydrogen fuel very quickly. A star with 25 times the mass of the Sun might live fast and die young, living only a few million years before running out of fuel. Our Sun, by contrast, is expected to live up to 10 trillion years before it meets its own demise. But when a massive star exhausts its supply of hydrogen, it begins to fuse heavier and heavier elements. First comes helium, then carbon, oxygen, neon, and finally iron. Each step produces even more energy until the star becomes a true titan. It shines with a brilliance that dwarfs our Sun, but this too is a double-edged sword. The tremendous energy output of these giant stars is matched by an equally immense energy requirement. And when the star reaches iron, it hits a wall. Iron is the most tightly bound nucleus of all, meaning that fusing it requires more energy than it provides. In effect, the star's engine grinds to a halt.
Ow!
Without the outward push of fusion, the star's core begins to collapse. The speed of this collapse is nothing short of astonishing. As the core contracts, it does so at a speed close to 18,000 kilometers per second. That's 65 million times faster than the speed of sound in air. This incredible acceleration is driven by the relentless force of gravity. And as the core careens toward oblivion, it heats the surrounding material to unimaginable temperatures, triggering a shockwave that blasts outward. This is the supernova explosion. It's a cataclysmic event that briefly outshines an entire galaxy. But within the star's core, the collapse is far from over. The core continues to contract, this time at a speed that defies comprehension, reaching 90% of the speed of light. It's a realm where the rules of physics, as we know them, begin to break down. In this extreme environment, the core reaches a density that's 1 trillion times greater than that of atomic nuclei. At this point, the very definition of matter breaks down. Electrons are crushed into protons, turning the core into a soup of neutrons. This neutron-rich environment is supported by a new type of pressure known as neutron degeneracy pressure. Imagine a crowded party. If the room expands, people can easily spread out. But if the room starts shrinking, people will feel the squeeze and resist by pushing against one another. Similarly, neutrons in a neutron star exert a pressure that resists further collapse. But this pressure has its limits. If the core's mass exceeds 3.5 times the mass of the Sun, even neutron degeneracy pressure cannot prevent further collapse. When this happens, the core continues to shrink, reaching densities that are a mind-boggling 100 trillion times that of atomic nuclei. In this extreme state, The core is squeezed to a single point known as the singularity, and around this singularity lies the event horizon, the boundary of no return. Crossing the event horizon means venturing into a region from which nothing, not even light, can escape. Beyond the horizon, the rules of physics as we understand them cease to apply. Space-time is stretched and distorted in ways that defy our intuition. Time itself slows to a halt, making the event horizon a place of eternal darkness and mystery. But the story of black holes doesn't start only with dying stars. Evidence suggests that the very first black holes may have formed in the infancy of the universe itself. These so-called primordial black holes could have emerged from density fluctuations in the hot, dense plasma just moments after the Big Bang. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes could range from microscopic sizes to masses greater than entire stars. If they exist, they might help explain some of the mysteries of dark matter and the unseen scaffolding of the cosmos. Later, as the first stars ignited in the universe around 200 million years after the Big Bang, black holes began forming from their explosive deaths. Some of these early black holes quickly grew, feeding on surrounding gas and merging with one another, creating the seeds of supermassive black holes that would eventually anchor entire galaxies. One of the most compelling theories about how supermassive black holes grow in the early universe involves a process known as accretion. Imagine a black hole not as a lone wanderer, but as a cosmic glutton, constantly seeking to expand its mass. In the early universe, the intergalactic medium was a rich soup of matter and radiation. As black holes moved through this primordial sea, they acted like cosmic sieves, pulling in the surrounding matter and adding it to their growing mass. This process was not a gentle one. The matter consumed by black holes did not simply vanish, but was heated to millions of degrees, emitting a brilliant light that illuminated the darkness of the early universe. These brilliant flashes were not merely beautiful spectacles, they were the key to unlocking the growth of the earliest galaxies. As black holes feasted on the intergalactic medium, they also gathered and compressed gas and dust, creating the building blocks of the first galaxies. In fact, black holes became the engines of creation, driving the formation of the very structures that would eventually harbor stars and planets. This process of accretion has continued throughout cosmic history. Even today, supermassive black holes are found at the hearts of most galaxies, including our own Milky Way, and they continue to grow by consuming surrounding matter. As black holes grow and consume matter, they shape their surroundings in profound ways. Their immense gravity distorts and magnifies the light from distant sources, creating a cosmic lens that allows us to see extremely distant galaxies. These gravitational lenses not only reveal the power of black holes, but also serve as windows into the distant past, allowing us to glimpse galaxies as they were billions of years ago. Black holes also play a crucial role in regulating star formation within galaxies. Their powerful gravity influences the distribution of gas and dust, affecting the rate at which stars can form. In this way, black holes act as cosmic gardeners, shaping the very environment in which stars are born and evolve. But despite their destructive and shaping power, black holes can also be cradles of creation. In the extreme environment around a black hole, matter is heated to unimaginable temperatures, giving rise to some of the most energetic phenomena in the universe. These conditions trigger the production of heavy elements that are the building blocks of planets and life itself. In this way, black holes, while terrifying in their destructive power, also play a vital role in the chemical evolution of the universe, seeding the cosmos with the elements that make life possible. Black holes are not just cosmic oddities. They are integral parts of galaxies, influencing everything from star formation to the distribution of elements in the universe. Understanding their life cycles helps us unravel the very evolution of the cosmos. The birth of a black hole is the birth of a paradox, an object that both hides information and yet reveals profound truths about the nature of reality. And this is just the beginning of our journey. In the grand theater of the cosmos, black holes are both the main character and the unseen force that drives the plot.
Yes.
Their presence, though invisible, is announced by the telltale signs they leave behind. And we, the audience, are both fascinated and terrified by their dramatic entrances. Yet there's another twist to this cosmic tale. Imagine if amidst the gas and gravity, amid the starlight and supermassive cores, There existed something even more enigmatic than black holes themselves, something that challenged our understanding of reality. Enter the most dangerous black holes in the universe, not in terms of size, but in terms of the questions they pose. First, let's recall the rule of cosmic etiquette. You don't discuss a black hole's weight unless you're planning to feed it. Otherwise, bring up its singularity and face the consequences. To navigate this delicate situation, we turn to our most powerful tool, math, specifically Einstein's general theory of relativity. It tells us how gravity should work in the vicinity of a black hole. But here's the catch. It breaks down at the singularity. This is the heart of the black hole, where our current understanding of physics simply stops making sense. Here, gravity becomes infinite. Space-time curves infinitely. Matter is crushed to infinite density. It's the ultimate singularity. But if we set aside the singularity, the theory works surprisingly well. It accurately predicts how black holes warp space, how they affect nearby objects, and even how they grow over time. However, poking and prodding these predictions with observations hasn't always yielded smooth sailing. For instance, there are some black hole candidates whose masses are so large that they seem to mock the limits of physics. One such rebel is the black hole at the center of the M82 galaxy, which weighs in at a staggering 300 billion solar masses. Now, if you think that's impressive, consider this. In the relatively small M82, this means there's a lot of mass packed into a tiny space, so much so that if it were any larger, gravity would pull it back in on itself. The sheer compactness of this black hole challenges our understanding of how such a massive object can exist without collapsing in on itself. It's as if a mountain were floating above the ground. Physics tells us it should fall, but somehow it doesn't. Similarly, at the heart of the NGC 4038 and 4039 galaxies lies a giant known as the antennae galaxies. And right in the middle is a colossal black hole weighing in at 100 billion solar masses. With such a massive black hole residing in a comparatively small space, it defies the expected pattern. Usually, the bigger the black hole, the larger the host galaxy. But in this case, the ratio is way off. But the weirdness doesn't stop there. If these black holes were plopped down in an empty universe, they wouldn't just sit there twiddling their thumbs. Oh, they would start gobbling up any nearby matter, including gas and dust. Yet observations show that both M82 and NGC 4038, 4039 have plenty of gas around their black holes. How do these gas reserves stay put? One possibility is that the black holes might be surrounded by a protective bubble of some sort. This bubble could shield the gas from the black hole's relentless gravitational pull. But the question remains, how does such a bubble form, and why doesn't it collapse under its own weight? The issue is not just theoretical curiosity. It touches on a fundamental question. How does matter behave in the extreme conditions near a black hole? While Einstein's theory tells us what should happen, observations suggest something else is going on. The difference might lie in quantum effects, those weird rules that govern the subatomic world. At very small scales, quantum mechanics takes center stage, and it plays by a different set of rules. It introduces probabilities, uncertainties, and even the possibility of multiple realities. These quantum oddities could play a role in creating the bubbles that keep the gas from falling into the black hole. Or maybe there's something else at play, some unknown force or particle that we haven't discovered yet. The point is, when we push the boundaries of our knowledge, reality has a way of surprising us. Now, if you thought those were mind-boggling conundrums, hold on to your space helmets, because we're about to blast off to even more perplexing puzzles. Here's the thing. According to the laws of physics, black holes shouldn't emit anything. They're black, after all. They absorb everything that ventures too close, including light. Yet some of them seem to glow with an eerie red light. It's not a bug, it's a feature, or at least scientists think it is. What they're seeing is a phenomenon called superradiance. Imagine a group of friends standing around a campfire. If each person only emits a small amount of light on their own, they might blend into the background. But if they all start to sync their movements, suddenly they become impossible to ignore. That's because when things sync up in the quantum world, the combined effect is much larger than the sum of the individual parts. This amplification is called superradiance, and it happens near some black holes. The light they emit isn't exactly visible light. It's stretched by the black hole's gravity until it falls into the infrared range. Scientists believe that this glow comes from clouds of supercooled gas hovering just outside the event horizon. These clouds are not your typical fog. They are so thin that each cubic centimeter might contain only a handful of atoms. They are kept in check by the black hole's gravity, which balances the outward push of radiation pressure. When these conditions come together, superradiance kicks in, boosting the light emission to detectable levels. But there's more to the story. The light emitted from these clouds is not uniform. It has complex patterns that could hold clues to the behavior of matter in extreme environments. It's a treasure trove for scientists looking to unravel the mysteries of quantum physics and gravity. If black holes were nothing more than invisible voids in space, they would be difficult to imagine, let alone study. Yet the universe has given us glimpses. Signatures carved into light, gas, and gravity that reveal their presence. Some of these black holes have become iconic, not just for science, but for human culture, representing milestones in our quest to understand the cosmos. But while we've made incredible progress, we've barely scratched the surface. The most dangerous black holes are not just cosmic powerhouses, they are riddles wrapped in event horizons. They challenge our understanding of reality, pushing the boundaries of physics. As we continue to probe the depths of space, we'll undoubtedly encounter more of these cosmic enigmas. Each one will test our theories, refine our observations, and bring us closer to a deeper understanding of the universe. Remember, we are not just observers, we are participants in a grand cosmic adventure. Every new discovery, every perplexing puzzle, every mind-bending mystery is a step on our journey to unraveling the fabric of reality. So let the black holes challenge us, let them confound us, and above all, let them inspire us. For in their enigmatic depths lies the key to unlocking the secrets of the cosmos. Our Milky Way contains millions of black holes. Most are relatively small, but some weigh millions or even billions of times as much as our sun. As nearby stars pass close to these giants, they can be flung into a wild ride around the black hole. Under certain circumstances, these journeys take the stars on a closed path, and the stars wind up trapped in an orbit that keeps them eternally circling their invisible captor. These special orbits are called the ergospheres of the black hole, and the stars confined within them are destined to travel for eternity. In some ways, these objects are similar to the strange stars found in science fiction, such as the infamous neutron star known as the lighthouse in the film Interstellar. However, while the properties of these fictional objects are not rooted in physics, the astrophysical counterpart known as a quasar is among the most energetic objects in the entire universe. Although the term quasar was coined in 1964, these peculiar objects were first identified in the 1930s when astronomers noticed bright points of light amid distant nebulae. When studied with telescopes and radio waves, these bright points of light appeared to be fixed in position. However, when examined with visible light telescopes, the same objects seemed to move. It wasn't until the late 1960s that the true nature of quasars became clear. Astronomers realized that these enigmatic objects were not stars at all, but rather powered by supermassive black holes at the center of distant galaxies. Quasars are among the most luminous and distant objects we can see, allowing astronomers to use them as probes of the early universe. Since the discovery of quasars, the study of active black holes has come a long way. But the truth is, we still know very little about them. Despite decades of research, many of the most important questions about active black holes remain unanswered. For example, exactly how do black holes grow and evolve over time? What role do they play in galaxy formation and evolution? And how do they influence the behavior of the gas and stars around them? While we do not currently have all the answers, recent years have seen a number of exciting developments in our quest to understand active black holes. We have witnessed incredible views of materials swirling around a black hole and new insights into the growth and evolution of these enigmatic objects. As we continue to study active black holes, we can expect to learn more about some of the most fundamental questions in all of physics. Moreover, with the advent of new and improved telescopes, we are poised to make even greater discoveries in the years to come. Indeed, active black holes are among the most fascinating and mysterious objects in the entire universe. And the more we learn about them, the more we realize just how much there is left to explore. Black holes are not just fascinating objects of study in their own right, they also play a crucial role in our understanding of the evolution of galaxies. Supermassive black holes are thought to be at the heart of most galaxies, including our own Milky Way, and these behemoths can grow by consuming gas, dust, and even other black holes. As a black hole consumes matter, it releases huge amounts of energy in the form of light and heat. This energy can drive powerful winds and jets that shape the surrounding galaxy. By studying the effects of black holes on their host galaxies, astronomers can gain insight into the coevolution of black holes and galaxies. Furthermore, black holes play a critical role in the life cycle of galaxies. As galaxies collide and merge, their central black holes can come together, creating a larger black hole. This process can trigger a burst of star formation in the galaxy, and can also play a role in the formation of the galactic structure we see today. By understanding how black holes influence the dynamics of galaxies, we can better understand the large-scale structure of the universe. In addition to their influence on galaxies, black holes also have a profound impact on our understanding of physics. Their extreme gravity creates conditions that allow us to test our theories of gravity and quantum mechanics like never before. By studying black holes, we can learn more about the fundamental laws of nature and push the boundaries of our scientific knowledge. Perhaps most importantly, black holes are simply one of the most awe-inspiring phenomena in the universe. Their immense power and enigmatic nature have captured the imagination of scientists and the public alike. And as we continue to explore these objects, we can be sure that they will continue to amaze and inspire us for generations to come. Black holes are not just distant and mysterious objects. They are an integral part of our universe that shape the world around us in ways we are only beginning to understand. The enigma of black holes, however, does not end there. These celestial objects raise fundamental questions about the nature of reality and the limits of human knowledge. One of the most perplexing mysteries surrounding black holes is the question of what happens to information that falls into one. According to the laws of quantum mechanics, information cannot be destroyed. Yet once something crosses the event horizon of a black hole, it is impossible to retrieve. This apparent paradox has led to some of the most mind-bending theories in physics, such as the idea that black holes have a fuzzy boundary known as the event horizon, which allows for the possibility that information may be stored on the surface. Others have suggested that black holes are connected to other parts of the universe through wormholes, which could potentially allow information to escape. Despite these intriguing ideas, the true fate of information in a black hole remains one of the biggest unsolved problems in modern physics. But black holes do not exist only in the abstract realm of paradoxes. They are intimately tied to the history of galaxies, and even to the story of our own planet. Many galaxies, including our own Milky Way, are believed to harbor supermassive black holes at their centers. And these giants can have a profound impact on the evolution of their host galaxies. When a star ventures too close to a supermassive black hole, it can be ripped apart in a process known as spaghettification. This dramatic event can trigger a burst of star formation in the galaxy, leading to the birth of new stars and planets. In our own galaxy, the supermassive black hole at the center is thought to have played a key role in regulating star formation and shaping the Milky Way as we know it. Understanding the role that black holes play in galaxy formation and evolution is a major focus of research in astronomy today, and recent discoveries have revealed some surprising insights. For example, astronomers have found that black holes can actually help to protect galaxies from the destructive forces of cosmic rays. By emitting powerful jets of material, black holes can create a protective bubble around their host galaxies that shields them from harmful radiation. This unexpected discovery has led to new theories about how galaxies evolve over time and has highlighted the importance of black holes in the universe. Despite the progress that has been made in recent years, there is still much that we do not know about black holes. With the advent of new telescopes and other observing facilities, we are poised to make even greater discoveries in the years to come. One of the most promising areas of research is the study of gravitational waves, which are ripples in the fabric of space-time caused by the acceleration of massive objects. Gravitational waves provide a unique window into the most violent and energetic events in the universe, such as the collision of two black holes. By detecting gravitational waves, we can learn more about the properties of black holes and the nature of gravity itself. Another exciting area of research is the study of black hole mergers, which occur when two black holes spiral inward towards each other and eventually collide. These mergers are among the most cataclysmic events in the universe and provide an opportunity to test our understanding of gravity and the nature of space-time. As we continue to explore these and other mysteries, we can be sure that black holes will continue to captivate and inspire us for generations to come. Black holes are a testament to the awesome power and mystery of the natural world. They remind us that there are still many things that we do not know, and that there is always more to discover. As we continue to explore the depths of space, we can be sure that black holes will continue to captivate and amaze us. From the smallest particles to the largest galaxies, the universe never ceases to amaze. Black holes are a reminder of the beauty and wonder of the cosmos, and a source of endless fascination for scientists and dreamers alike. So let us continue to explore the mysteries of the universe and push the boundaries of human knowledge. Who knows what wonders we may find there? The idea of an infinitely dense point in space, with gravity so strong not even light can escape it, was considered crazy. Until Albert Einstein confirmed its possibility in 1915. 100 years later, black holes are still a wild frontier for astronomers, particle physicists, and cosmologists. Here's what we do know. Black holes are regions in space from which nothing can escape. Once something crosses a black hole's event horizon, there's no turning back. Not even light, which travels at the fastest speed possible, can escape the black hole's clutches. Everything that ventures to close is pulled beyond the horizon and into the unknown depths. To understand what happens next, let's start at the edge of the horizon, where the pull of gravity is extreme. As an object approaches a black hole, the gravitational force it experiences increases dramatically. This intense force stretches and distorts the object in a process known as spaghettification. The near-infinite gravity gradient between the head and feet can be hundreds of millions, even billions times greater than Earth's gravity. Eventually, the forces become so great that they rip the object apart at the atomic level. Once broken down to subatomic particles, these particles continue their journey into the heart of the black hole. As they descend, they accelerate due to the increasing gravitational pull. This acceleration causes the particles to collide with each other, creating a tremendous amount of heat. The temperature of these particles as they approach the singularity can reach billions of degrees. At this point, the particles can no longer exist and are reduced to pure energy. As the energy approaches the singularity, it creates an intense bright glow. This region around the black hole where light is emitted is known as the accretion disk. The accretion disk is one of the most spectacular and deadly features of a black hole. The intense heat and radiation emitted from the disk can be thousands of times brighter than a typical galaxy. As the energy reaches the singularity, it is compressed to an infinitely small point. At the singularity, all known laws of physics break down. Our current understanding of physics cannot describe what happens at this point, leaving scientists with more questions than answers. So how do we actually detect black holes if we can't see or measure them directly? We observe their effects on nearby matter. By studying how stars and gas move around a black hole, astronomers can estimate its mass and size. Also, as mentioned earlier, black holes can be indirectly observed through their accretion disks, which emit large amounts of light and radiation. Additionally, the gravitational waves created by the merger of two black holes provide evidence of their existence. How do black holes form? While the exact mechanism varies, they generally arise from the gravitational collapse of massive gas clouds. Over time, these clouds contract under their own gravity, forming dense cores. As the cores continue to collapse, they heat up, creating a hot, dense ball of matter. When the pressure and temperature reach extreme levels, nuclear fusion begins, giving rise to new elements and forming stars. These stars grow by gathering surrounding gas and dust until they reach several million times the mass of our sun. As they exhaust their fuel, these massive stars collapse under their own gravity, creating a black hole. What's the connection between black holes and dark matter? Dark matter is an elusive substance that makes up a significant portion of the universe's mass. While we can't see dark matter directly, its gravitational effects on visible matter provide evidence for its existence. Similarly, black holes, although invisible, can be detected through their gravitational effects on nearby matter. Some astronomers hypothesize that dark matter could play a role in the formation and growth of black holes by providing an additional source of mass that influences their behavior. However, the exact relationship between dark matter and black holes remains uncertain. Can anything escape from a black hole? The answer is yes. Surprisingly, not even black holes are entirely inescapable. Certain particles and radiation can escape from the intense gravity near a black hole's event horizon. This phenomenon is known as Hawking radiation, after Stephen Hawking, who predicted its existence in 1974. Hawking radiation occurs due to quantum effects near the event horizon. Particles can be emitted from the surface of the horizon, carrying energy away from the black hole. This means that black holes are not entirely black. They emit a faint glow due to Hawking radiation. However, the temperature of this radiation is extremely low, and it is difficult to detect. The existence of black holes has left astronomers with more questions than answers. One major unanswered question is, how do black holes form? While we understand that they form from the collapse of massive stars or the accumulation of large amounts of matter, the exact mechanisms are still being explored. Another pressing question is, how do black holes interact with their surroundings? Studying the effects of black holes on galaxies and the distribution of matter in the universe provides valuable insights into their behavior and helps us understand the evolution of the cosmos. Are black holes truly eternal? Some theories suggest that black holes can evaporate over time through Hawking radiation. However, the process is incredibly slow and would take billions of years to occur. Furthermore, black holes can grow by consuming matter and merging with other black holes, which raises questions about their ultimate fate. Understanding the life cycle of black holes is crucial to unraveling the mysteries of the universe. With the launch of the James Webb Space Telescope, we are equipped with a powerful new tool to explore the cosmos. This advanced telescope enables astronomers to observe previously unseen details of the universe, including the behavior of black holes. JWST's infrared capabilities allow us to see through dust clouds, providing a clear view of regions where stars are born and black holes reside. By observing the light passing through these areas, scientists can study the properties of black holes and their impact on the surrounding environment. Black holes are truly fascinating astronomical objects that continue to captivate scientists and stargazers alike. Their mind-boggling properties and mysterious nature have sparked countless questions and debates. What's inside a black hole? Can we travel through a wormhole? Are there multiple universes beyond the event horizon? While we may never have all the answers, the pursuit of knowledge about black holes drives scientific exploration and pushes the boundaries of our understanding of the universe. Black holes, those enigmatic cosmic entities where gravity is so strong, not even light can escape their grasp. They've captivated scientists and the public alike for decades. But did you know that for much of history, black holes were considered mere mathematical curiosities, existing only in theories and equations? Today, however, the narrative has shifted dramatically. We've gone from skepticism to awe and wonder as we've transformed black holes from abstract predictions into real, tangible objects. So join us as we embark on a journey through time, exploring the incredible story of how we went from thinking black holes could impossibly exist to understanding that they are a fundamental part of our universe. Our story begins in the early 20th century, when Albert Einstein developed his groundbreaking theory of general relativity. This theory revolutionized our understanding of gravity, no longer seeing it as a force, but rather as a curvature in the fabric of space-time caused by mass and energy. According to Einstein's equations, massive objects distort the very essence of space and time around them. This distortion, or curvature, dictates how other objects move in their vicinity. As a result, planets orbit stars not because they're pulled by a mysterious force, but because they follow the curves in space-time created by the star's mass. This was a radical departure from the prevailing view of gravity as a force, and it opened up a whole new way of thinking about the universe. However, the implications of general relativity didn't stop there. One of its most intriguing consequences was the prediction of a new type of celestial object. A region in space where gravity was so intense that not even light could escape its clutches, a black hole. The idea of black holes initially met with skepticism and disbelief. They seemed outlandish, too extreme to be taken seriously. Many scientists dismiss them as mere mathematical oddities with no physical counterpart. Einstein himself was among the first to doubt the reality of black holes, believing them to be an artifact of his equations rather than a true phenomenon of nature. Despite the doubts, scientists continued to explore the properties of these enigmatic objects. They realized that black holes would not just be massive, they would also possess a radius, known as the Schwarzschild radius, which marked the boundary of no return. Once something crossed this radius, it could never escape the black hole's gravitational pull, not even light. It was as if a celestial drain had been placed in the universe, silently consuming anything that ventured too close. Yet black holes remained invisible, hidden from human detection. They were like ghosts haunting the universe, their presence felt but never seen. But as the years passed, evidence began to mount, suggesting that these ghostly objects might actually be real. Then came the 1960s and the dawn of the space age. Rockets and satellites now allowed humans to see the universe in a whole new way, as one that wasn't limited by the constraints of Earth's atmosphere. This opened up an entirely new way to observe the cosmos. Among the many discoveries made during this era, one stood out as particularly groundbreaking. But the discovery of Cygnus X1 raised as many questions as it answered. Could a black hole really exist? How could we prove it? And what other mysteries lay hidden in the depths of space? As the evidence for black holes grew, the scientific community began to accept their existence. In the following decades, telescopes like the Chandra X-ray Observatory and XMM Newton mapped dozens of black hole candidates, showing that these enigmatic objects are scattered throughout the cosmos. No longer confined to the realm of mathematics, black holes became a tangible part of our universe, albeit still shrouded in mystery. In the late 20th century, another line of evidence emerged, pointing to the existence of giant black holes lurking at the centers of galaxies. By studying the motion of stars near the heart of the Milky Way, astronomers discovered an invisible mass 4 million times heavier than our Sun. This extraordinary find provided compelling evidence for the presence of a supermassive black hole at the center of our galaxy. Today, we know that supermassive black holes are not just theoretical concepts or mathematical curiosities. They are real, tangible objects that play a crucial role in the evolution of galaxies. Then came the early 21st century, and perhaps the most groundbreaking confirmation of all: the discovery of gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, announced the first-ever detection of gravitational waves, ripples in space-time predicted by Einstein over a century ago. These waves were generated by the collision of two black holes more than 1 billion light-years away. The detection of gravitational waves not only validated Einstein's theories, but also provided an entirely new way to observe the universe. Through gravitational waves, we can listen to the sounds of the cosmos and learn about objects and phenomena that were previously beyond our detection methods. With each passing year, the evidence for the existence of black holes became more compelling. They evolved from being considered merely mathematical possibilities to becoming recognized as fundamental components of our universe. But there was still something missing: a direct visual observation, a glimpse into the abyss. And that's when the Event Horizon Telescope came along. This global collaboration linked radio telescopes around the world, creating a virtual Earth-sized telescope. In 2019, the EHT team published the first-ever image of a black hole, the glowing ring of M87*. 3 years later, they unveiled the image of Sagittarius A*, the supermassive black hole at the center of our own Milky Way. These weren't just remarkable scientific achievements. They were a testament to human curiosity, ingenuity, and our relentless pursuit of knowledge. Today, black holes are no longer some abstract concept or a figment of mathematical equations. They are real, tangible objects that we can observe and study. The journey from skepticism to acceptance and eventual discovery is a profound reminder of the power of scientific inquiry. It shows that what once seemed impossible or even absurd can become a cornerstone of our understanding of the universe. It's a lesson that goes beyond the realm of science, reminding us that limitations and naysayers should never stifle our curiosity or our pursuit of knowledge. As we continue to explore the mysteries of the cosmos, let the story of black holes inspire us to push the boundaries of what we think is possible. Embrace the unknown, question the established, and never lose sight of the wonders that await us in the grand theater of the universe. The quest to understand black holes has not only transformed our understanding of the universe, but has also pushed the boundaries of human ingenuity. From developing advanced telescopes to creating new technologies, the study of black holes has driven innovation and discovery across multiple scientific disciplines. Moreover, the global collaboration involved in projects like the Event Horizon Telescope have fostered international partnerships in a shared pursuit of knowledge, uniting scientists from different nations in a common goal. The impact of black holes extends beyond the scientific community, captivating the public imagination and inspiring awe and wonder about the mysteries of the universe. The efforts to observe and understand these enigmatic objects have sparked a sense of unity and shared curiosity among people from all walks of life. And as we peer deeper into the cosmos, we must also turn our attention to the potential dangers posed by these celestial giants. Supermassive black holes, while fascinating to study, can also pose a threat to the very existence of our civilization. Their immense gravitational pull can disrupt planetary systems and their energy emissions. It can wreak havoc on Earth's delicate balance. Understanding and predicting the behavior of these cosmic behemoths is crucial for ensuring the long-term survival of humanity. As we continue to unlock the secrets of black holes, we must also consider the ethical implications of our discoveries. The pursuit of knowledge for its own sake should not come at the expense of potential risks. Striking a balance between scientific advancement and responsible exploration will be a challenge for future generations. In conclusion, the incredible story of black holes serves as a testament to the boundless curiosity and spirit of exploration that drives humanity forward. From their theoretical origins in Einstein's equations to their confirmation, through gravitational wave detection and direct imaging, black holes have captured our imagination and inspired countless scientific advancements. As we continue to unravel the mysteries of these enigmatic objects, we must also consider the challenges and ethical questions they raise. The potential threats posed by supermassive black holes and the responsibility that comes with wielding the power to probe the unknown are issues that demand our attention and careful consideration. Nevertheless, the allure of the cosmos and the pursuit of knowledge for the betterment of humanity will continue to drive us forward. Just as our ancestors looked up at the stars and wondered about the nature of the universe, we now have the ability to explore those wonders in ways they could have never imagined. The story of black holes is a reminder that the universe never ceases to amaze, and that our journey of discovery is far from over. As the 21st century progresses and humanity's technological might grows, it's clear that we are entering a brave new world. The very fabric of society and daily life is transformed by things such as artificial intelligence, genetic engineering, and virtual reality. These marvels were once the stuff of science fiction, but have become a tangible reality thanks to advances in technology. Yet while these modern innovations shape our lives in big and small ways, there is another phenomenon that looms on the horizon, poised to redefine our existence in a way nothing else can. It's a force so powerful that not even light can escape its grasp. It's a realm where time and space are distorted beyond recognition. It's a frontier that promises to unlock the deepest secrets of the universe and redefine the very limits of human potential. Yes, it's the enigmatic world of black holes. You might be thinking, wait, this sounds dramatic. Are we going to get sucked into a black hole? Well, not to worry. We're here to explore how black holes won't just shape our collective future, but may hold the key to individual advancement. How can we use them to achieve what seems impossible and rewrite the rules of reality itself? Join us as we embark on an exhilarating ride through the uncharted territories of the cosmos. Together, we'll unravel the mysteries that lie within these celestial enigmas and discover the profound impact they will have on our existence in the decades ahead. So let's start with a simple question. What exactly are black holes, and why should we care? Well, imagine squeezing a massive star many times the size of our sun, until it's just a few miles wide. Then picture the incredible gravitational pull that would result from such a dense concentration of mass. Now, you've got a black hole, a region in space with gravity so strong that nothing, not even light, can escape its clutches. But black holes are more than just cosmic oddities. They represent a gateway to a world of possibilities. By studying them, we gain insights into the fundamental laws of physics and the nature of reality itself. And with advancements in technology, we're now able to observe and understand these enigmatic objects in ways that were once deemed impossible. So how will black holes shape our future? Let's delve deeper into 3 areas where these cosmic wonders are poised to make an impact. First, black holes may hold the key to unlocking a nearly unlimited source of energy. Imagine harnessing the immense power of a black hole to generate clean, sustainable energy. It sounds like a far-fetched idea, but it's actually closer to reality than you might think. Theoretical physicist Roger Penrose has proposed a way to extract energy from a black hole's rotational energy known as the Penrose process. By dropping matter into a black hole's ergosphere, a region just outside the event horizon, we could siphon off some of its spin and release tremendous energy. This process could provide an almost inexhaustible supply of power, potentially solving our energy needs for centuries to come. Furthermore, black hole accretion disks, the swirling masses of matter around black holes, emit intense radiation as they spiral into the abyss. This radiation could be harnessed to power spacecraft and other technologies, allowing us to explore the cosmos in ways that were previously unimaginable. But the implications of black holes extend far beyond energy production. They also offer a tantalizing glimpse into the very nature of space and time. Black holes challenge our understanding of reality by warping the fabric of space-time to such an extreme that they create shortcuts through the cosmos known as wormholes. While wormholes remain purely theoretical, the idea of traveling through them to reach distant parts of the universe or even other dimensions is incredibly appealing. Imagine being able to traverse the galaxy in mere seconds, or even jumping to different universes. It's a concept that seems straight out of science fiction, but it's rooted in the very real physics of black holes. Additionally, black holes themselves could hold clues to the nature of dark matter and dark energy, to mysterious phenomena that make up a significant portion of the universe but remain poorly understood. By studying black holes, we can learn more about these enigmatic forces and their role in shaping the cosmos. And finally, black holes have the potential to unlock new frontiers in computing and data storage. At the heart of a black hole lies an event horizon, a boundary beyond which nothing can escape. This raises intriguing questions about the nature of information and whether it can truly be destroyed. Some physicists believe that information is conserved, and that it's possible to retrieve data from within a black hole. This has led to speculation that black holes could be used as a kind of cosmic hard drive to store vast amounts of information. Moreover, the extreme conditions near a black hole could lead to the development of new forms of computing that are far more powerful than anything we have today. Just imagine the possibilities if we could harness the power of quantum mechanics to perform calculations at the speed of light. So you might be wondering how we're going to turn all this science fiction into a tangible reality. Well, the answer lies in the relentless pursuit of knowledge and the unwavering spirit of human exploration. We are entering a new era of discovery, driven by groundbreaking technologies and ambitious projects that are pushing the boundaries of what we thought possible. Take, for example, the Event Horizon Telescope, a global collaboration of researchers who have come together to capture the first ever image of a black hole's event horizon. This remarkable achievement was made possible by combining data from 7 radio telescopes around the world to create a virtual, Earth-sized telescope. It's just one example of the incredible feats we're capable of when we set our minds to exploring the unknown. Another promising avenue of research is the development of quantum computers, machines that harness the mind-bending properties of quantum mechanics to perform calculations in ways that are impossible for traditional computers. These machines could revolutionize fields such as medicine, materials, science, and cryptography by solving problems that have long been considered intractable. And it's not just in the realm of technology that we're making strides. We've also launched ambitious projects to explore our cosmic surroundings. The James Webb Space Telescope, for instance, is poised to revolutionize our understanding of the universe by peering deep into space to uncover the secrets of the cosmos. With its advanced instruments and unprecedented sensitivity, the Webb telescope will allow us to see farther, deeper, and more precisely than ever before. So the future looks bright for those who dare to dream big and push the boundaries of what's possible. But amidst all this excitement, it's important to remember that with great power comes great responsibility. As we delve deeper into the mysteries of black holes, we must proceed with caution and respect for the forces we're dealing with. After all, we're dealing with phenomena that can distort space and time, warp the fabric of reality, and consume anything that ventures too close. It's a sobering thought, but it's one that should inspire us to proceed with wisdom and care. By understanding the risks and benefits of exploring black holes, we can ensure that we harness their power responsibly and ethically. It's a tall order, but it's one that we're up to. After all, we've always been fascinated by the unknown, and our curiosity has led us to some of the most incredible discoveries in history. Black holes are no exception. And as we continue to explore their mysteries, we'll undoubtedly find ways to harness their power for good. So what does this mean for you? Well, as the frontiers of knowledge expand and new technologies emerge, you'll have the opportunity to be part of something truly special. You'll witness firsthand the incredible discoveries and innovations that will shape the future. But it's not just about being a passive observer. You can also play an active role in shaping this brave new world. By educating yourself about the incredible power of black holes and the amazing work being done to unlock their secrets, you'll be better equipped to make informed decisions about the future. You can also support organizations and initiatives that are pushing the boundaries of exploration and discovery. Every contribution, no matter how small, can help advance our understanding of the universe and bring us closer to harnessing the power of black holes for the betterment of humanity. In the end, it's not enough to simply marvel at the mysteries of the cosmos from afar. We must embrace the spirit of adventure and discovery and boldly go where no one has gone before. So that's the only way we'll be able to unlock the incredible potential of black holes and harness their power to create a better future for ourselves and generations to come. So are you ready to join this exciting journey? Are you eager to explore the uncharted territories of the cosmos and discover the secrets that lie within? If so, then it's time to take action. Educate yourself, support bold initiatives, and most importantly, never lose your sense of wonder and curiosity about the universe and its infinite possibilities. Who knows what incredible discoveries await us just beyond the event horizon? The future is yours to shape. Cosmos is calling, and it's up to us to answer. Are you ready to take the first step towards a brighter, more enlightened future, powered by the very essence of the universe itself?